Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will discuss our last topic for the chapter, which is reaction mechanisms. So let's go ahead and get started. Now, when you guys were studying chemical reactions in first semester of general chemistry, you may have developed an idea that when two or more reactant particles come together, such as these two reactant particles, a chemical reaction will take place that will automatically produce the product in one step. And so a balanced chemical reaction gives off this illusion that the conversion of reactants to products will always take place in one step. And so in reality, that is not true. There are many chemical reactions out there that requires many sub-steps before the final product is produced. And so this is where reaction mechanisms come in. And so reaction mechanisms are a collection of elementary steps. And these elementary steps provide the reader or the audience a better insight as to how the reactants gets converted into products during the course of a chemical reaction. So let's go ahead and take a look at the reaction mechanism for this example. So here we have dinitrogen tetroxide reacting with fluorine gas to produce 2 moles of nitrile fluoride. And so it turns out that the reaction mechanism for this overall chemical reaction involves 3 elementary steps. And so for any given chemical reaction, the amount of elementary steps required for reactants to be converted into products is unique for that chemical reaction. And so basically what I'm trying to say is that some chemical reactions will only require 1 elementary step. Some chemical reactions will require 2 elementary steps. And the list goes on and on and on. And so looking at the reaction mechanism for this specific example, the first elementary step tells us that dinitrogen tetroxide must be converted into 2 moles of nitrogen dioxide. And so already the first step is telling us that this reactant, which is present in the overall chemical equation, does not actually interact with fluorine gas directly to produce the product. It must be converted into this reactive intermediate. And so typically the product of the first elementary step or the second elementary step and so forth and so forth. So the product of the elementary step typically becomes the reactant for the next elementary step. And so it turns out that only 1 mole of nitrogen dioxide is going to interact with a second reactant that's found in the overall chemical equation, this fluorine gas. And the product of the reaction between these two will produce a fluorine radical and 1 mole of nitrile fluoride, which is what we're trying to create in this chemical reaction. And so this fluorine radical, which is a reactive intermediate, then becomes the reactant for the third elementary step, such that this fluorine radical will interact with the second nitrogen dioxide that was formed in the first elementary step to produce the second mole of this nitrile fluoride compound. Another common trend that you guys will see with reaction mechanisms is some type of indication of the rate of the chemical reaction. And so looking at this column, EA is the activation energy. And so if you recall from a previous lecture video, the activation energy, when you're comparing it among different types of reactions, or in this case, different elementary steps, gives us an idea of how fast each elementary step is going to occur. And so the higher the activation energy, the slower the rate of that chemical reaction or that elementary step. And so the smaller the activation energy, the faster that elementary step will take place or will happen. And so for this very specific example, we can actually sketch a potential energy diagram that describes the conversion of dinitrogen tetroxide into the final product. And so when you guys are drawing these potential energy diagrams for reaction mechanisms, let me go ahead and draw a straight line here. The axis is going to be very specific. And so here we have potential energy on the y-axis. So I denote that as PE. And the progress of the reaction is described on the x-axis. And so if you guys recall, the potential energy of your reactants will be fixed at a certain level. It does not start from zero. And so simply because there is potential energy stored in the chemical bonds inside a chemical compound. And so let's just say that I have this reactant, so N2O4. And according to my first activation energy, it's going to increase by 59 kilojoules per mole. And so I'm just going to roughly estimate 59 kilojoules per mole. So I'll go ahead and just put an arrow and say 59 kilojoules per mole. That's my activation energy. And then this is going to describe my first transition state. So my first transition state is reflective of the transition state that's happening in the first elementary step. And so this reaction mechanism does not tell us if the elementary step is exothermic or endothermic. And so I'm just going to arbitrarily move this curve downwards until I get to, some value or some potential energy level. At this point in time, it actually does not matter. And so here at this point, you guys are going to write the product of the first elementary step, as well as the reactant for the second elementary step. And so this is going to be NO2 and F2. And so notice that the reactant gets written, the reactant for the first elementary step gets written first, and then you're going to describe the transition state. And finally, when you go down that hill, when you hit that valley, so to speak, you're going to write down the product of the first elementary step as well as the reactant for the second elementary step. And so looking at this activation energy that was quantified for us, it looks like it's going to increase by 83 kilojoules per mole. And so I'm just going to sketch that. Let me see here, let me draw this wider. And so this is going to be the second transition state. And the height of this to this is going to be 83 kilojoules per mole. So notice how I didn't start my 83 kilojoules from down here. I started it at the same potential energy as where my valley takes place. Okay. And so once again, at some moment in time, it's going to fall back down. I have really no information to tell me how low I go, so I'm just going to, draw it in a arbitrary amount. And so in the last elementary step, or the third elementary step, it looks like I have this fluoride radical, this fluorine radical, and one of the products, FNO2, and I also have NO2 that's being produced. And so I'm just going to go ahead and write F plus NO2, which is going to describe the reactant of the third elementary step. And so since I form one of the products, I'm just going to put at the bottom of this FNO2. Okay. So looking at the activation energy, it's about 9 kilojoules per mole. And so I'm just going to go ahead and draw a small hill, a very small increase, so that it's reflective of 9 kilojoules per mole. And so this is going to represent the third transition state. And this example doesn't actually tell us if it's exothermic or endothermic, so I'm just going to make it up. I'll just say that this reaction is cold to the touch. And so if it's cold to the touch, then that lets me know that this reaction is endothermic. And so since it's cold to the touch, that means that the potential energy of the products must be much higher than the potential energy of the reactants. So notice how the height of the potential energy of the reactants is much lower than the height of the potential energy of the products, which is characteristic of endothermic reactions. And so the products that I'm going to write down is simply going to be 2 moles of FNO2. Okay. And so looking at this potential energy diagram that we sketched, you can see that the second elementary step has the highest peak, or tallest hill, if you will, letting us know that the second elementary step is going to take the longest. So it's the rate determining step. All right. And so let's go ahead and talk about the elementary steps in greater detail. And so elementary steps are individual steps in the reaction mechanism, as we've already seen. And so elementary steps can be described by their molecularity. And so I'll go ahead and further elaborate on what molecularity is and why it's useful for determining whether or not a reaction mechanism is plausible. And so the molecularity can be identified as the molecularity of the elementary steps can be identified as unimolecular, bimolecular, and termolecular. And once again, we'll look at what these mean in just a second. And so it turns out that an elementary step may be fast and reversible, or just fast and going in one way. And so, for example, here we have this double-headed arrow. So this is telling us that this reaction can reach an equilibrium very quickly. And so it's important for us to identify these fast, reversible elementary steps, because when we start learning how to write the overall rate law based on the rate laws from the elementary steps, we can make this relationship, the rate of the forward reaction is equal to the rate of the reverse reaction, to help us to come up with the overall rate law from the elementary steps. And we'll see that a little bit later. And so elementary steps can be slow. And if you have an elementary step that's really, really, really slow, then that elementary step can, or not can, but is the rate determining step, which is abbreviated as RDS. And so the rate determining step implies that that specific step has the largest activation energy compared to all other elementary steps. And so notice that elementary step 2 has the highest activation energy, and therefore elementary step 2 would be considered the rate determining step, which can be once again observed in a potential energy diagram. And so the reason why this is important is because the rate determining step, or the RDS, determines or defines the overall rate of the reaction. And when we start going through some problems, we'll also learn that the rate determining steps allow us to write the backbone of the overall rate law for the entire chemical reaction. And we'll see that once again a little bit later down the line. And so the one thing that you guys do need to know about rate laws with respect to elementary steps is that the order of reaction for the elementary steps can be determined by simply using the coefficient in the equation that's written. And so that was something that, that's unique to reaction mechanisms. And so if you recall in a previous lecture video, I've mentioned that you typically do not use the coefficients from the overall balanced chemical equation to determine the order of the reaction. And typically, to determine the order of reaction, it has to be proved experimentally. And you can figure it out by using the technique called method of initial rates. However, when you're talking about reaction mechanisms and writing the rate laws for each individual elementary steps, since these elementary steps do not describe the overall chemical reaction, it is okay for you guys to use the coefficient in front of that compound to determine the order of reaction for that specific elementary step. And so, for example, in the forward direction, since there is an invisible 1 in front of dinitrogen tetroxide, we can go ahead and conclude that the order of reaction in the forward direction for this specific compound is first order. Now, when you guys are looking at this reaction in reverse, notice that there's a coefficient of 2 in front of nitrogen dioxide. So if you're trying to write the rate law in the reverse direction, the order of reaction with respect to NO2 is going to be second order. Okay? And so it really makes things a lot easier in terms of writing the individual rate laws for these elementary steps. But once again, you guys cannot use the coefficient from the overall chemical reaction to write the overall rate law for this chemical reaction. All right, and so I'll go ahead and repeat that as we continue this lecture video. All right, so let's go ahead and talk about molecularity. And so molecularity allows us to identify or classify specific elementary steps. And so elementary reactions can be described by their molecularity, and the molecularity is a reflection of the number of reactant particles in that specific step, not in the overall step, but just that specific elementary step. And so let's go ahead and talk about the different types of molecularity that's possible. So we have something that's called unimolecular. And so a unimolecular basically describes that you have one reactant particle. And so you guys can go ahead and identify the molecularity of the forward reaction, which might be different than the molecularity of the reverse reaction. And we'll look at that in just a second. So if this is an elementary step, notice how there's only one reactant particle. And so therefore, this specific elementary step is unimolecular. And so when you guys are writing the rate law for a unimolecular elementary step, let me just put in here elementary step to remind us that this is not describing the overall rate law, rather it's just the rate law for the elementary step. Okay. And so when you guys are writing the rate law for unimolecular elementary step, it's basically the rate of the chemical reaction is equal to the rate constant K times that by the concentration of that specific compound raised to the first power. Okay. All right, so let's go ahead and talk about bimolecular elementary steps or bimolecular reactions. So bimolecular implies two reactant particles. And so if you guys are looking at some of these examples, notice that here you have one reactant particle and a different reactant particle. But overall, you have two reactant particles. And so there's another way for you guys to get two reactant particles, which is two of the same compound. Now, when you guys are writing the rate law for these elementary steps for a bimolecular reaction, remember that the order of reaction can be written based on the coefficient of each elementary step. So since there's one reactant A and one reactant B, then the order of reaction with respect to A is 1, and the order of reaction with respect to B is 1. Okay, so remember, once again, these are elementary rate laws. Now, if you guys are looking at this next one, notice how there's 1 and 1, but since they are the same, technically it's 2. And so therefore, the order of reaction with respect to A for this example is second order. And so termolecular means a combination of 3 reactant particles. And there are many, many ways in which we can describe an elementary step that has 3 reactant particles. And so we can have 3 different reactant particles, or 3 of the same reactant particles, or 2 of the same reactant particles, but one of them is different. And so overall, we can go ahead and write the elementary rate law by simply using the coefficients of the elementary step. So here we have 1, 1, and 1. And so therefore, this is first order, first order, first order. Here we have 1, 1, 1, but they're all the same. So technically, this is third order. Here we have 1 and 1. Two of them are the same, so this is second order, while reactant B is first order. Okay. All right, so let's go ahead and see how we can apply this in a reaction mechanism that we've already seen. And so looking at the first elementary step, I want you guys to notice that there's only one reactant particle in the forward direction. So in the forward direction, this would be considered unimolecular. However, since this is a reversible reaction, if you look at this equation in reverse, there's two reactant particles. And so therefore the reverse is bimolecular. Okay. And so looking in the forward direction, for the second elementary step, I have 1, 2 reactant particles. And so in the forward direction, this would be bimolecular once again. Okay, so hopefully you guys can see the pattern that I'm working towards for molecularity. Now, there's another reason why we pay attention to molecularity of elementary steps. So the molecularity kind of reflects the likelihood that those reactant particles will collide in an efficient way. So it has to follow collision theory. So remember, for collision theory, let me see if I have room. No, I don't. So let me just write it over here. And so remember that in collision theory, there are three parts to it. The reactant particles have to collide. They have to have the proper orientation. And they have to have sufficient kinetic energy so that it overcomes the activation barrier or the activation energy. And so once all three of these are fulfilled, then the collision amongst those reactant particles in each elementary step would be considered an effective collision. The product would be formed. And so the plausibility, for example, one reactant particle to have the correct orientation and have the correct amount of kinetic energy that's required to overcome an activation energy, to overcome the activation energy, is likely to happen, right? So it's something that's likely to happen. And so unimolecular reactions or unimolecular reactions can occur in real life, right? You have one reactant particle, and that reactant particle has a high probability that it will fulfill all three of these conditions. So for a bimolecular reaction, in which you have two reactant particles, we have to consider the probability that those two reactant particles will collide. And when they do collide, how likely is it that they'll have the proper or the correct molecular orientation? And how likely is it that they'll have enough kinetic energy to overcome the activation barrier? And so, the probability becomes less than unimolecular, but it is possible. And so for unimolecular and bimolecular, these types of molecularities for elementary steps are plausible. However, once you start getting into termolecular, in other words, 3 reactant particles, or even 4 or 5 reactant particles, the probability that all three particles will collide at the same time and have the proper molecular orientation and have enough kinetic energy to overcome the activation barrier becomes highly unlikely. And so when you guys are trying to rationalize whether or not a reaction mechanism is possible, if you have an elementary step that is termolecular, there are some red flags that's going to be raised. And so in reality, there's only, I believe, if I recall correctly, like 2 or 3, or just a very, very small handful of known chemical reactions that actually is termolecular. And so it is more likely that unimolecular and bimolecular elementary steps is most likely to happen. And termolecular and any reactant particles higher than 3, so 4, 5, 6, the list goes on, is more unlikely to occur. And so it's easier for two reactant particles to collide that has the correct orientation and has enough kinetic energy to overcome the activation barrier versus 3 reactant particles versus 4 reactant particles, and so forth and so forth. So this molecularity is important for us to understand with collision theory kind of backing it up, right? And so when you guys are trying to prove whether or not a reaction mechanism is possible, you have to take in consideration the molecularity of all of the elementary steps. All right. So let's go ahead and talk about another topic, which is reactive intermediates and catalysts. And I've kind of brought up reactive intermediates a little while ago. So let's go ahead and put a definition to this. And so reaction intermediates are typically generated in one elementary step, and then it's consumed in a later step. Whereas catalysts gets consumed in the very first step, typically gets consumed in the first step, but then it's regenerated in the last step. So let's go ahead and take a look at this proposed mechanism for the depletion of ozone by Cl. And so looking at the product in green, this ClO is a reactive intermediate. The reason why ClO is a reactive intermediate is because it gets generated, so it gets produced in an elementary step and then consumed in the next elementary step. Okay. Whereas a catalyst is consumed in the first step and then later produced in the last step. Because remember, catalysts do not overall get consumed in the chemical reaction. And so if you label a substance a catalyst, you should be able to get the catalyst back after the reaction has ended. Okay. So Cl is an example of a catalyst. Okay. Now, if you were to take the sum of all of the individual steps, the Cl is going to cancel this Cl, and the ClO is going to cancel the ClO, producing or leaving you with just ozone, O3, and oxygen. And then for the products, notice how there are two oxygens that do not cancel. And since they are the same, you just simply add them together, and that's how you get two O2 molecules. Okay. And so the same thing can be said in the very first step. So notice that NO2, when you guys add up all of the individual elementary steps, the NO2 here, so these two NO2s will cancel with this two NO2. The F will cancel with the F. The radical fluorine will cancel with the radical fluorine. And what you're left with is dinitrogen tetroxide and F2, fluorine gas, as your reactants. And here, since you have two of the same products, then you have 2 moles of product at the very end. Okay. So I just wanted to point that out as we're working through this idea of reaction mechanisms. Okay. So we have elementary steps, we have molecularity, we have reaction intermediates or reactive intermediates, and we have catalysts. And so overall, now that we've built up our understanding and our foundation of reaction mechanisms, how can we apply it? And so one way that you can be presented with a problem on a worksheet or an exam is to prove if a reaction mechanism is plausible. And so for it to be plausible, it must meet 3 criteria. And so all 3 of these must be checked off. So first, the molecularity of each elementary step is plausible. And for now, we're just going to bank on unimolecular and bimolecular reactions. And so if your elementary step is either unimolecular or bimolecular, then that elementary step is plausible, and you can go ahead and check the first point off. And so the sum of all elementary steps must match letter by letter, number by number, the overall or net chemical reaction. And we kind of saw that in the previous 2 examples. And last but not least, the mechanism itself must produce an overall rate law that's consistent with an experimentally determined rate law. And so it's this last step or this last criteria that we have not yet really talked about in greater detail, and that's what we're going to do next. And so before we do that, let's go ahead and take a look at this proposed mechanism. Once again, if you look at the first elementary step, we have 2 reactant particles, and so this would be a bimolecular. And if you look at the second elementary step going the forward direction, it's also bimolecular. And so if you guys look at the reverse, this is also bimolecular, as well as the final product for the second elementary step. And so since all of the elementary steps in this proposed mechanism is bimolecular, then that means that we can go ahead and check off this criteria because the elementary steps are plausible. It's likely for these 2 reactant particles to collide, and when they collide, they have the proper orientation as well as the kinetic energy to overcome the activation barrier. And so if we add up the elementary steps, does it match the overall chemical reaction? And we saw that it does a little while ago. So when you add all of this up, the Cl's will cancel, the ClO's will cancel, leaving you with just ozone and this radical oxygen and 2 moles of O2. And so since the sum of the elementary steps does match the overall or net chemical reaction, we can go ahead and check this part off. And so once again, we're now going to move on to the last criteria, and I'm going to go ahead and explain it in greater detail, which is determining the rate law from a proposed reaction mechanism that would be experimentally consistent. That would be consistent with what was experimentally determined. Apologize for that. All right, and so we're going to start learning how to determine the overall rate law from a reaction mechanism, not using method of initial rates, etc. And so there's 2 types that we're going to cover: reaction mechanisms with a slow initial step and reaction mechanisms with a fast initial step. And so we're going to go ahead and start with reaction mechanisms with a slow initial step. And so we're going to consider the following reaction. Here we have 2 ICl, 2 moles of ICl, reacting with hydrogen gas to produce diatomic iodine and 2 moles of hydrogen chloride in gas state. And so it also told us that from the experiments that was done, they were able to determine the rate law. And the rate law is that the hydrogen gas is first order and ICl is first order. So I'll go ahead and just write that in. I'll ink that. So first order reaction. And so this question is asking us whether or not this reaction mechanism is plausible. And so this is the proposed reaction mechanism. And so to determine if this reaction mechanism is plausible, it has to fulfill these 3 criteria. So first, let's look at the molecularity. And so it looks like the molecularity for the first elementary step and the second elementary step, they're both bimolecular. And so therefore, the molecularity does check out. And so the second thing that we need to check is whether or not the sum of all elementary steps matches the overall chemical reaction that's provided. And so this is the overall chemical reaction. And so if we add both of these elementary steps together, we should be able to come up with the overall chemical reaction. So let's go ahead and go through this. Here we have H2. Notice that H2 is present. And here we have 2 ICl. And so notice that there's 2 ICl. And on the product side, I have I2. Here's I2. And then 2 HCl. So there's 2 HCl's here. And so the only thing that I have not boxed is HI. Okay? And so it turns out that hydrogen iodide in its gaseous form is going to be a reactive intermediate, not a catalyst. The reason why HI is a reactive intermediate is because it gets produced from an elementary step and it gets consumed in the next elementary step. So this is gone and then this is gone. So when we add both of these elementary steps, we get H2 gas plus 2 moles of ICl in gas state. And this produces I2 diatomic iodine in gas state and 2 moles of hydrogen chloride in gas state. And so I'm not saying that this is hydrochloric acid, because hydrochloric acid would then infer it's aqueous, but it's gas state, so it's hydrogen chlorides. So that name will suffice. So notice that this and this matches, this and this matches, this and this matches, this and this matches. And so we've now checked off the first 2 criterias. And so the last criteria is determining whether or not the reaction mechanism, determining whether or not the rate law from the reaction mechanism is consistent with the experimentally determined rate law. Okay. And so to do that, we're going to go ahead and kind of break down this mechanism to incorporate the rate of the reaction for each elementary step. And so in this example, the activation energy, the value of the activation energy was not given to us. It simply is stating that this is the slow step and this is the fast step. Okay. And so if you recall a little bit earlier, the rate law, the overall rate law, can be determined from the rate determining step, the RDS. And the RDS is the slowest step in the reaction mechanism. And so what you want to do is you want to first build your foundational rate law, for lack of a better term, based on the slowest elementary step. And so since we have a slow initial first step, that means that the first step is rate determining. And therefore we can go ahead and write the rate law based on the RDS as the rate of the reaction is equal to some rate constant K times this. And so I want you guys to remember that the rate law incorporates or just involves only the reactants. And so the reactants in the forward direction is simply H2 and ICl. So here we have H2 gas raised to the first power because we have a coefficient of 1. And we're going to multiply this by the concentration of ICl. And once again, it's raised to the first power. It's first order because there's only 1. And so I want you guys to recall that we can only use the order of reaction, or we can only use the coefficient from an elementary step to determine the order of reaction for that very same elementary step. Okay. And so since this is the rate law for step 1, the first elementary step, and it turns out that this first step is the rate determining step. And so if step 1 is a rate determining step, the rate law that you wrote from it, or you got from it, is equal to the overall rate law. For that chemical reaction. And so let's go ahead and compare that with the rate law that was determined experimentally. And so notice that the rate law that's determined experimentally is the same as the rate law that we derived from this reaction mechanism. And so since we've proved that the rate laws are the same between experimental and theoretical, then we can go ahead and check off that last criteria. And since we can check off all three criterias, we can conclusively say that this mechanism is plausible. Okay. All right. And so we're going to go ahead and take a look at reaction mechanisms with a fast initial step. And we're going to see how we can develop the overall rate law for reaction mechanisms with fast initial steps. And so here we have the overall reaction 2NO plus O2 to produce 2NO2. And they told us that the experimental rate law is this guy. And so we're going to go ahead and just kind of go through the motions, very similar to what we did in the previous example. And we're going to try to determine if this reaction mechanism is plausible. And so the first thing that we're going to look at is the molecularity. And so notice that the molecularity for the first step in the forward direction is bimolecular. Now, looking at the reaction arrow, notice that it's double-headed. It goes forward and reverse. And so the molecularity for the reverse, meaning NO3 being converted into NO and O2, is going to be unimolecular. And so since none of them is termolecular, the possibility for this reaction mechanism to occur, or the possibility for the first elementary step to occur, is okay, it's good. And so looking at the second elementary step, in the forward direction, we can say that it is bimolecular because we have two reactant particles. And so just for kicks, if we wanted to determine the molecularity for the second step in reverse, since there are two reactant particles, it's also bimolecular. And so since both elementary steps are either bimolecular or unimolecular, then both these elementary steps are plausible. Now let's go ahead and check to see if the sum of the elementary steps will give us the overall chemical equation. And so here I have NO and NO. I have two NOs. Let me just go ahead and highlight them. So I have two NOs, so that checks out. I have one O2, that checks out. I have two NO2, so that checks out. So the only thing that I did not highlight is the NO3, because NO3 is a reactive intermediate. And so if it gets produced in one elementary step and gets consumed in the next elementary step, then you really won't see it in your overall chemical equation. And so the second criteria for proving if the reaction mechanism is plausible can be checked off. In other words, the sum of the two elementary steps does equal the overall chemical equation. And so the last step is to determine whether or not the theoretical rate law from the proposed reaction mechanism does produce the reaction mechanism that was experimentally determined. And so to do that, we're going to have to rely on our rate determining step. So notice that the rate determining step is not the first step, rather it's the second. And so we are going to develop the foundation of our rate law based on the rate determining step, which happens to be step 2 in this example. And so to write the rate law, well, let me keep that. So to write the rate law, we're going to look at the reactants for step 2. And so here, let me see if I can just write it again. Okay, so 2, here we have NO3. I'll leave some space. And we have NO. And we have 2 NO2. All right. So we're going to write the foundation of our overall rate law based on the rate determining step, which happens to be step 2. So therefore, the rate of the chemical reaction is equal to the rate constant K times this by the concentration of NO3, which is a reactant. And so since the coefficient is 1, this is first order, times this by the concentration of NO, which is our second reactant in the second elementary step. And it's going to be raised to the first power. All right. And so looking at the rate law that we just wrote, notice that it does not match the experimental rate law. So does that mean that this proposed mechanism is incorrect? Actually, it doesn't, because if you guys are looking at the rate law, the foundational rate law that we just wrote, one of the reactants is actually not even present in the overall chemical equation. And so what that means is that we are not yet done. So we cannot have a reactive intermediate in our rate law. And so that means that we have to substitute it somehow with another term. Okay, so let me just write that up here. So must substitute with a compound that's present in the overall chemical reaction. Okay. And so how do we do that? Well, to do that, we're going to rely on the previous step. So notice how this reactive intermediate is consumed in the second step, but produced in the first step. And so if we can somehow make this substitution between the first and the second step, then we'll be able to represent NO3 in terms of the chemical compound that's only present in the overall chemical equation, specifically the reactants. And so let's go ahead and take a look at the first step, and I'll rewrite the first step on the next slide. So we have, step 1, so elementary step 1. we have NO and O2 gas. And notice how it's a double-headed arrow. Okay? And it'll produce NO3. And so, since this is a fast step, it's going to reach an equilibrium very quickly. And so this equilibrium is going to represent, so an equilibrium in a chemical reaction can be reached when the rate of reaction of the forward direction is equal to the rate of the reaction in the reverse direction. And so this is cool because now we can go ahead and use this definition of equilibrium to, it's going to serve as our foundation to create some assumptions. And so remember that the rate of the reaction can be described by the rate law, such that the rate of the forward is equal to the rate constant K times this by the concentration of NO raised to the first power times this by the concentration of O2 raised to the first power. Right? And so I got this portion from my reactants in the forward direction. And this is to the first. Okay? And so I can go ahead and do the same thing for the reverse. And so I can say that the rate of reaction in the reverse direction is equal to the rate constant K times this by NO3 raised to the first, once again, because I have a coefficient of 1. And so these, let me see here, these individual rate constants, I should expand it just a little bit more. So this K represents the rate constant of the forward direction, and this rate constant represents the reverse direction. Now, instead of saying forward and reverse, one way that you guys can represent forward and reverse is 1 and -1. And so if you have +1, that's representing something that's going in the forward direction. And then if you have -1, that's representing something that's going to the reverse direction. Okay. And so I can go ahead and clean up my work so that the rate in the forward direction is equal to the rate constant K in the forward direction times this by NO raised to the first power times this by O2 raised to the first power. Okay. And so I can clean this up and say that the rate of the reverse, which is -1, is equal to K -1, the rate constant of the reverse reaction, times that by the concentration of NO3 raised to the first power. And so the really cool thing about what we just did is we've kind of expanded on the definition of the rate of the reaction. And so what we're going to do is we're going to take the definition of the rate of the reaction and put them equal to each other, right? And so if the rate of the forward is equal to the rate of the reverse, then their definitions are also equal to each other. And so to put this together, I have K1 times this by NO raised to the first times O2 times raised to the first is equal to K negative 1, which is the rate constant in the reverse, times this by the concentration of NO3 raised to the first. Now remember, the main goal for doing all of this madness is to somehow get rid of this reactive intermediate in this foundational rate law that's dictated by the rate determining step. And so since NO3 is our reactive intermediate, that's the term that we want to solve for in this specific set of process. And so we're going to go ahead and solve for NO3, and to do that we're going to divide K negative 1 to both sides. And I'm going to just put the K negative 1 where the other rate constant is. And so therefore, what we get is the rate constant of the the rate constant of the forward direction in the first elementary step. Divide this by the rate constant in the first elementary step that's going in reverse, times this by the concentration of NO raised to the first, times this by the concentration of O2 raised to the first, which is equal to the concentration of NO3 raised to the first. So now that I have a definition for NO3, I'm going to go ahead and take all of this. Let me see if I can zoom out. I'm going to go ahead and take all of this and plug it into this term. Okay. And so I'm going to go ahead and just copy this real quick. Put this down here. Let me erase some stuff. And so I'm going to substitute all of this into here. And just to be consistent with the numbering, remember that this rate constant K came from the second step. So I'm just going to say K2. Okay. And so K2, which is the rate constant in the forward direction for the second elementary step, is being multiplied by all of this other stuff that I boxed. So let me go ahead and just write that in. So the rate of the chemical reaction is equal to K2 times this by the rate constant in the forward direction from the first elementary step over the rate constant for the first elementary step that's going in reverse, times this by concentration of NO raised to the first, times this by the concentration of O2 raised to the first, which equals 2. Oh, actually, it doesn't equal to anything. And I'm missing one more item. I'm missing this. Okay. All right. And so basically, all of this came from this term. And so the last thing that I'm going to do is just simplify. And so to simplify, I'm going to take all of my individual rate constants. So individual elementary rate constants. And when they come together, they form the overall rate constant for the entire chemical reaction. So you don't have to worry about subtracting or dividing or whatever. They just become the overall rate constant because we're now describing the overall rate law. And so this and these two terms are the same. So I'm going to go ahead and multiply this by NO raised to the second power times this by O2 raised to the first power, which is what's remaining. So this is the overall rate law that was derived from the reaction mechanism. And so notice that the overall rate law, maybe I should change colors. The overall rate law is rate is equal to K times that by NO raised to the second power or second order times that by O2. And so does this rate law match the rate law that we get? And the answer is yes. And so therefore, this reaction mechanism is possible. And so looking at the key differences between this example and this example is that the rate determining step is the first elementary step. So whenever your elementary step, or I'm sorry, whenever your rate determining step is the first elementary step, the rate law that you typically write or obtain is the final rate law for the overall chemical reaction. However, when your first step is a fast step and your second step is a slow step or the rate determining step, then deriving the overall rate law based on the reaction mechanism gets a little involved, right? And so the first thing you want to do is you want to write the backbone, if you will, of your overall rate law based on the rate determining step. And you'll see that the backbone of that rate law contains a reactive intermediate. And so that will infer, or that will guide you to think that you have to do something else to get rid of the reactive intermediate in your rate law. And so to do that, you'll have to use the previous fast step, which contains the same compound, that will contain the same compound, so that way you can substitute it out. And so here since our fast step reaches equilibrium very quickly, we can say that the rate of the forward reaction is equal to the rate of the reverse reaction. And we can go ahead and expand that by writing the rate law. So the rate of the forward reaction is equal to this, and the rate of the reverse reaction is equal to this. And so you're going to go ahead and put them equal to each other. And then you guys are going to solve for the reactive intermediate. And once you solve for the reactive intermediate, then you can go ahead and plug this into your rate law that was found from the rate determining step. So I'll go ahead and put a note over here. So this is going to be the rate law from the RDS. And so once you substitute these pieces in, you guys are just going to simplify, and all of your individual rate constants just becomes the overall rate constant, right? And if there are any terms that are similar, then you're going to put them together to create one term. And then whatever is remaining, you just write it down. And so this is the overall rate law. And if you look, NO and O2 is both present in the overall chemical reaction. So there's no more NO3. All right. So that's pretty much it for this lecture video. Hopefully you guys have kind of understood my train of thought, my logic. I'm just going to go ahead and solve this one without a video. And if you guys have any questions, you guys can either email me or talk to me about it during office hours virtually. All right, see you guys later. Bye.